Hi everyone, thank you for joining today's webinar. I am Chilla, and today we have here Ethan Reiter from Mantle and MJ Belmont from Westminster Tool with us, presenting Unlocking Conformal Cooling Software Design Hardware Build. Ethan Reiter is the Director of Marketing at Mantle. He has an extensive experience in technical marketing for design and manufacturing products. He previously ran the technical marketing team at Desktop Mantle, a 3D printing manufacturer focused on volume production. Before that, Ethan worked on the rapid prototyping team at MIT Lincoln Laboratory, where he worked on the laser communication system for the NASA Orion mission. MJ Belmont is the business development and project manager at Westminster Tool. He has been with them for 8 years, establishing a long and diverse foundation in the injection molding technical knowledge. MJ's experience over the years includes exposure to almost every area of the business, from marketing operations, quoting to project management. Today, his focus lies on the customer experience, helping customers overcome their biggest molding problems with comprehensive project oversight.
Great. Thank you for that introduction. And thanks for joining us, everyone. Let me go ahead and share my screen. Can everyone see that okay, hopefully? MJ, can you see that? Cecilia?
Yep.
Awesome. Awesome. So thanks everyone for joining. Thanks for that introduction. My name is Ethan Reiter. MJ's on the line here as well, and we'll kind of be going back and forth here. Today we're going to be talking about conformal cooling, software design, and of course Moldex 3D, and then hardware built and how you actually build these conformally cooled inserts. Quick agenda for today, and of course feel free to send any questions as you have them. I can actually be looking live as well as at the end we'll look at them, but we'll start with a quick introduction to Westminster Tool. We'll talk about why use conformal cooling at all and some of the benefits. We'll look at how you actually fabricate these tools. It's one thing to have them in digital across on the camera, but I'll talk about a couple things and how our technology actually works. We'll look at some examples, or MJ will share some examples from work that they've done. And then, of course, we'll do questions and answers at the end. So with that, let's go ahead and jump right in, and I'll turn things over here to MJ. Thanks.
Great. Thanks, Ethan. So yeah, first, let me introduce about Westminster Tool for those of you who are not familiar with us. Primarily, we are an injection mold builder, typically in the Class 101 medical field. I would say about 90% of our tools are somewhat medical device or anything basically in regards to the medical field. So with our molds, we're typically in the range of up to 6,000 pounds, and we're really diving into your parts challenges. So we're really looking at those complex, intricate geometries, tight tolerances, where some plastic might be plus or minus 1 thou, where our steel, due to stack-up tolerances, we might be dealing with plus or minus tenths. So we are capable of guaranteed to hold plus or minus 2 tenths. And you can see some of the applications we've dealt with in the past, from two-shot, micro, some micro parts that are smaller than a pellet, resin pellet, multi-cam with 45-degree angles, unscrewing both servo and hydraulic, insert molds, both like extruded tubes or metal needle inserts, and we've done some collapsible cores as well, primarily with the Hasco. We also have Mantle's first beta H13 3D printer. We partnered with them back in 2018, 2019, where we both collaborated together, and Mantle would send us pieces to do some testing on, and we'll provide them feedback. And what really stood out with us with Mantle, which I'm sure Ethan will get into, is just the stability and the surface finish that we get right off the printer from it. We do some molding as well, primarily low volume. Typically in the aerospace industry, we are Torlon certified, so we do have a government contract where we mold some Torlon, Peak, Ultem, and then we do anywhere from, I'd say, 10 to maybe 100,000 parts if our customer needs it. Typically, it's not as a competition. It's more of to help our customer out where your press might not be ready when the tool is ready, but we have our press available and we're able to run you 10,000 parts to get your assemblies and stuff ready out to market. So I did mention we are Class 101 tool builder, but we are nationally recognized throughout the country for both our internal apprenticeship program called Westminster Academy and our culture. As a tool shop, you typically hear the average age of 50, 55 years old. We have an average age of 35 years old, and we also have a wait list of people trying to come in and work with us, which is unheard of in this industry now. Some of our value add services at the bottom, that's really where we really excel with our customers. We have a really robust DFM process. We use Moldex 3D, hence why I'm here today. And then we also offer reverse engineering, and we have 4 presses ranging from 100 to 350 ton for anywhere from FOT to MFAT. Good, Ethan. So rolling right into Moldex, what do we use it for? So right off the bat, no matter what, it doesn't matter if the customer says, no, I don't need Moldex. We still use it internally because we have found that it saves us costs in the back end. So I'll start with our design phase. So right off the bat in DFM, we're looking at the success of the part. So we're looking at any bad part design concepts, maybe the part's too thick or you're gating in the wrong area. So we're diving deep into the part itself. The second phase of that is our prelim, which is basically final, where we put everything together. You have your mold base, you have your stack up, you have your cooling, you have your venting, everything like that. And basically what we're doing is simulating what we expect to see with our current design of the tool and where we can add improvements or where we see some improvements might be made. A great example is to the right here. We had a customer with a very large TPE part. I'll get into it a little bit more, but we immediately flagged a risk of, hey, there's that blade insert. We can't get cooling there. It's very thin. What's going to happen if we run Moldex or Moldmax as the insert? And you can see in the picture, which Moldex was able to simulate for us, where the significant difference of up to 60 degrees in your steel temperature, which obviously would have a huge impact on your part quality. So risk mitigation is what we're looking at, and all of the different areas that cooling, gating, venting, like I mentioned earlier during prelim. The second area is troubleshooting. So sometimes we've had customers come to us saying, hey, this tool was built here, we just can't get it to validate. So we'll take it in, we'll ask for your process settings, we'll ask for the current design, and we'll run it in our Moldex software and try to replicate what the customer is currently seeing in real life. As long as if we're able to do that, that gives us the confidence and data to keep moving forward and start simulating different solutions that might be able to help mitigate or correct the current challenge that our customer is working for. So you got Moldex. What's conformal cooling? Why conformal cooling, right? So I see really for us, it's 2 areas. First is part quality. There's times where cooling, yeah, you hear cooling, it's going to reduce your cycle time, but that's not always the case. So what we have found is it is able to keep a consistent temperature in your steel around the part. I have a picture on the next slide that kind of helped us alleviate some of the challenges we were seeing where there was still molten plastic on this thick section. This was a nylon 33 glass filled part, where the first shot was actually okay, but as more and more cycles started coming, there's a core in that little diameter that you see facing you, where it would actually still be molten and would start pulling when the slide face came away. So what we did was we actually utilized our Mantle technology, had my designer throw in the most complex conformal cool lines that he could come up with. And sure enough, we were actually able to run this tool within 10 seconds, quicker than the current state. So Ethan, if you go to the next slide, kind of gives you a side-by-side what we were seeing with the traditional cooling lines, and then what you're seeing on the right-hand side is what you're seeing with those conformal lines you saw on that previous slide. So you can see around the part itself, you see that more of a lighter blue. What that's telling you is that steel around that part after, we'll say 50 cycles in this scenario, is a lot warmer than when we first started up at that first cycle. Now with conformal cooling, because you have a lot more turbulent flow, a lot more cooling, and throughout the part or throughout the cavity, you can see it stay in a consistent temperature even after the X amount of cycles that we reached. So instead of having hot spots to your left, we're actually more uniform throughout. So second, which is the most obvious when people hear conformal cooling, faster cycle time, right? So yes, you're going to get a faster cycle time. And how are you getting a faster cycle time? It kind of goes back to the last slide where you have a more consistent control of your steel temperature instead of the steel heating up as it continues to go. So what does that mean with a reduced cycle time? So first, obviously, you're reducing your tool cavitation that you might end up needing so if you say you were estimating 20 seconds and you need an 8 cavity tool, well, with conformal cooling, maybe you can get it down to 10 seconds. And then you can basically reduce your cavitation down to 6 or 4, and you're still able to reach that quantity. The other area where you're able to, that this benefits, is obviously press capacity. So the quicker the cycle time, the quicker you meet your annual volume for part quantities, the more space you have in order to continue to mold more tools. Because 9 times out of 10, a lot of the challenges I hear from my customers is, I don't have a press available right now. Can you mold this? So you can move forward, Ethan. So why, if conformal cooling has these benefits, it saves us money, it gives us better parts, less scrap, less warp, parts come off great, right? Why don't we use this on all of our projects, right? Well, Ethan, if you go to the next slide, typically before Mantle came, there were two options that we were using. There was brazing the steel, and then there was obviously metal 3D printing that we were using in the past, but both were very expensive. And even with metal 3D printing, you get it off the printer, your printer's going to be moving all over the place. So with that, that is really why we started looking more and more and diving more and more into 3D printing steels. And that's where Mantle came in. And Mantle helped us basically get a blank conformally cooled cavity for the same price as if we were going to get a traditional steel, blank steel component.
Awesome. Thanks. And that's a kind of perfect segue help automate your tool making processes by allowing you to really print mold components, inserts, tools, screws, bushings, etc., with really unmatched accuracy, surface finish, and tool steel performance. EDM, etc. And we'll show some examples of that. But if you look at traditional mold building process, which I'm sure many of you are familiar with, there's a lot of steps involved, from even just securing your raw material, securing your block, to doing the programming for the rough milling, to doing the fixturing for your hard milling after heat treatment, all the way through electrode design, electrode programming, actually producing the electrodes alone, and then all of those EDM steps involved before you of these steps. Any final finishing of squaring and polishing. So for example, I don't know how well this will come across on the screen, but an example of a printed insert where you're sort of getting this D2 level surface finish, sort of a matte sinker EDM finish. I don't know how well this is actually a Westminster Tool part here, but this is molded right out of a Mantle insert with no finishing done to the cavity. So you sort of get this sort of matte finish on the part that you're seeing here. So for the right applications, for a lot of applications, you're removing all of that EDM involved to produce ribs like you're seeing here. And all you're doing is printing that and then doing a little bit of grinding at the end. So we like to say Mantle automates anywhere from 50 to 85% of the process with the push of a button, because it gets you to this really with little to no effort from yourself. So what does the technology actually deliver? This kind of sinker EDM style finish, 1 to 3 micron RA, Charmy 26 or a D2, like that's a fine sinker EDM. Excellent precision, plus or minus 1 thou per inch. Important to know that if you need to go better on both surface finish or on precision, you can absolutely refine the parts like MJ was saying. You can machine it, you can polish it, you can burn it, etc. Getting EDM sharp features, I'll explain a little bit how we do this later, but 3 thou corner radiuses, stable, durable tool steels, both H13 and I should have added here 420 stainless steel as well. Very easy to use system, no programming required. And of course, like we're talking about today, that ability to incorporate conformal cooling in as well. It's great to have some fancy print processes, but what does it ultimately mean for you? Like we mentioned, or like MJ was mentioning, lower cost and less time to produce tools. On the left here is a tool from Hypertherm. It's actually a peak component. They were able to produce this slide at 75% less cost and less time. This is actually a dishwasher component for a large appliance OEM, 67% less cost, 71% less time. And then a good example of a medical device tool from MJ here and from West. Involved versus having to do all the steps. And as we know, the capacity of your tool room is so important. So they were able to reduce that by 65%. So ultimately, what does that deliver? It delivers the ability to incorporate conformal cooling without these time and cost penalties that were so commonly associated. Traditionally, the bar for conformal cooling was so high, the volume had to be so high, the part cost maybe had to be so valuable or things like that to justify using a conformally cooled tool, just because of all that added time and cost associated with these traditional methods of brazing. For the same price as you would traditionally, really lowering the bar to be able to incorporate conformal cooling.
Ethan,
yes.
Sorry, can I stop you for a second?
Sure.
Lots of our audience are saying that you're cutting in and out. Would you mind to turn off your camera? Sometimes that helps.
Yeah, thank sorry you. About that, everyone. Sorry about that. Hopefully enough came through here of this idea of really being able to use metal 3D printing technology like Mantles to deliver conformal cooling without a big time or cost penalty like you would with traditional technologies. A little bit about how the tech here, a printer and then a furnace, which is really where this line is kind of dividing the two. It all kind of starts with our metal paste. This is a flowable metal paste. So we don't use a powder like other metal 3D printing technologies. We don't use a filament. We're actually printing a paste, which is very similar to a toothpaste. That paste is a combination of metal powder mixed with binder and a solvent, similar to, so this kind of is what makes up your paste, and this is what we're actually printing. So during the printing step, the material is flowing. We're not actually heating the material. It's viscous enough that we're just using a pump to push it through a nozzle like you're seeing here. There's no loose metal powder involved in this process because it's all encapsulated inside of the paste, but we're just extruding this paste material through a nozzle like you're seeing here with a pump. After every layer is printed, we go through and dry the layer. We only need that solvent to make the material viscous enough that it can flow. So we come by and we dry the layer with heat and with air to remove that solvent out, just leaving behind metal powder and binder. At this point, it's firm. It's firmed up almost to about the same as a dense foam. And we come in and we actually machine the material. So this is why we're able to achieve those very, very crisp features, excellent surface finish, because we're actually machining it during the printing process, every single layer. It's very soft at this stage, so it's very, very easy to machine. We refine the finish, and we can actually incorporate some features that we wouldn't have been able to print initially because of the printing process. This is going to repeat every single layer. So as you can imagine, this enables us to do some very, very deep ribs because we're printing, machining, printing, machining, printing, machining. We don't have to worry about getting a tool deep down in the pocket or anything like that. We're able to do that on a layer by layer basis. After the printing is complete, we put the part into a furnace. If you're familiar with other sinter technologies like metal injection molding or press and sinter technologies, it's similar in that we're putting this metal powder and binder combination into a furnace. This first removes any binder that was left in the part, and the part densifies and shrinks. Shrinks about less than 9% in this process. Other sinter-based processes shrink more like 18 to 20%, but still this is where we're losing our tolerance. It's how closely can we predict how much this part is going to shrink during this process. But even with that shrinkage, we're able to achieve that plus or minus 1 thou per inch. The result is a part with no residual stresses. It's a dense isotropic material. You're able to, here's just a quick video of the printing. Hopefully this comes across okay. Video is always a little strange on shares like this, but that's just laying down the paste, coming through and drying the material where we're removing the solvent. And then finally the machining step to actually refine some of the features and improve the surface finish. Great. That just repeats over and over again. Inside of the furnace, it's a little harder to get a camera inside of a high temperature furnace, but essentially this is a big oven under controlled vacuum and some gas to control the atmosphere that sinters the part into a dense metal part after. The materials available, H13 tool steel, very common, durable workhorse material coming out of our process at a 42 HRC. It can be heat treated up to over 50 HRC, fully compatible with those traditional tooling operations as well, which I'll share after this. And then recently we just announced a 420 stainless steel. We announced this down at MPE. This is really an ideal material for corrosive molding environments and scenarios. Very, very common in the medical device industry, which is a lot of our customers, and we're really looking forward to this 420 stainless steel that you're seeing here as well. I mentioned this before, but fully compatible with traditional toolmaking operations, machining, polishing, texturing, welding, all of these processes. If you need to grind it, etc., you can polish it up to that A2 finish. You can texture it. You can even weld it. So if you need to go beyond what's capable with our process, it's certainly fully compatible to do that with traditional processes. One question we get all the time, and I just wanted to include one example of this that isn't necessarily a conformal cooling example, but is how durable is your material? Is it going to last? Is it a prototyping material? A lot of our customers ask that. Some of them actually wanted to put it to the test, where Tessie here has been running 2 different Mantle inserts actually in a 32 cavity tool for over 1.65 million cycles with no signs of unexpected wear. This is actually a deodorant component, so it's really, really high volume. And they also were still able to print the inserts and do the finishing involved weeks faster than conventionally. And this insert's still running, this number 1.65. We have to update every month or so, but this is just our great kind of gold standard of durability of the material to show that it is a equivalent material to the tool steels that you're using today. Awesome. I'll bring MJ back in here now to share some examples specific with Mantle and Moldex, of course, and how they're using conformal cooling.
Great. Thanks, Ethan. So yeah, I think I have 3 examples that we used conformal cooling / utilize Moldex in order to help state our case for our customer. So the first case study was with a medical contract manufacturer, and they had this existing two-shot tool where the current tool had some heating pipes that went into those 3 cored out areas in the bottom of the tool. With that, they were getting some shot-to-shot variance. There was significant warp that was now eventually getting out of spec for their FAI process. You can see the 2 areas where they're pointing at right there. So what we proposed to our customer, Ethan, if you can, there we go. So what we proposed to our customer was utilizing a conformal cooled core. So what the outcome was we actually reduced the cooling time by 10 seconds. So our customer reduced their cycle time, and then they also reduced the warp on those 2 areas. So the top handle area was reduced by a 5 thou less warp, and then the little tab that you see at the bottom, I guess bottom right, it was reduced by 3 thou. So two of the different Moldex simulations we used was first the part temperature. Ethan, if you can go to the next slide. So we ran a simulation to see what the well, obviously first, like I mentioned, we wanted to replicate what the customer was seeing. So that's what we did. We threw all the same exact process parameters as what the current tool was molding at, and was able to basically replicate what they were seeing. So you can see on the left, we used the part temperature of how hot that part was at ejection of the end of cycle versus with that conformally cooled core. So you can see a significant difference right here at the bottom, along with at the top of that flange or the handle there. So that was the first one. The second one on the next slide was more of the molten plastic, because we know that's what's really driving the warp. And you can see it pretty much got rid of just about all of that molten plastic that we saw from those heat pipes with that conformally cooled core. So with that gave us the confidence to propose this to our customer during our DFM phase, and we were able to actually move forward with this. Now, at the time, this was probably 6-7 years ago, so this was before we started talking with Mantle. We did end up moving forward this, but it had to be an upcharge, because obviously with conformal cooling at the beginning, like I said, it's a lot more expensive. The other thing we also had to do was increase the lead time. So once we got Mantle, we actually did a case study to see the difference between the two cores. So you can see the brazed approach took us 6 weeks, just over $1,800 per core, and the total lead time from basically once we got them in-house to complete was an additional 2.5 weeks. Now, we did the same thing with Mantle, where Mantle could have gotten a lot closer to that geometry, but we wanted to keep it as fair of a comparison. So we did the base state that you see on the top. So it took Mantle 2 weeks in total to print 8 cores, all on the same mold plate, and then obviously put it into the furnace to sinter. And that ended up being $1,100 each, and basically cutting the total lead time in half. So that kind of goes back to the case of why aren't we using conformal cooling on everything? Well, now with Mantle, that has allowed us to kind of get into that market field in order to help use conformal cooling. The other benefit of you having Mantle and these cheaper costs is we're able to actually start implementing this way up front before the production tool. We're able to implement this in your bridge tooling. We're able to utilize Moldex to simulate this to show you that, hey, this is an added benefit with it as well. So brazed is great. We've had great success with it. You can use it for any type of material, but if cost and lead time is an issue, then Mantle has been a huge benefit for us. So if you want to go to the next one. So this was an example of a customer had an existing tool. It was a single cavity pilot tool. It was actually this was a consumer part. It was a cosmetic part for the top of a makeup jar. They were actually going from compression molding to injection molding in order to begin the whole PCR recyclable materials and stuff like that. So cosmetic is obviously a big part. But as soon as we got the tool and the design and everything, we noticed, okay, first of all, the part has a poor design. The side walls were actually thinner than the top of the part, which, because you're going through that corner radius, it was actually causing the part to have a lot of splay and increasing the shear. So we asked the customer to keep it more uniform. So we increased that thickness, and then on top of that, we also improved the water lines. So if you go to the next slide, I can show you the Moldex simulations that we ran. So we found, one of the first things we found was to the right is the existing design. So you can see with the green that there really isn't that much turbulent flow. So you're basically getting hot spots in that bottom cavity. And that's where the customer was having a lot of issues, was at the top of the part, obviously, because that's where the end users are first off seeing. So what we did was we created new cooling lines. Both of them are more of a conformal, less traditional approach. You can see on the left, that is actually a hot drop or a gate insert for a valve gate. And we utilize Mantle's technology to get a conformally cooled, basically gate insert for that. You can see the red, that's obviously implementing the Reynolds number, showing you the significant spike in your turbulent flow. So you're able to keep the steel at a consistent temperature. And then at the bottom as well, you can see we did a little bit less traditional, where this one was more of, we just split the bottom cavity in half and then threw an insert in there so we could throw those lines in there as close as possible to that cap. So I should have put this slide before, but this again is kind of showing you, to the right is showing you what we saw more. This would be like an example of the DFM phase where we're focusing on the part. You can see on the top, you can see the significant warp, or the bottom, we're seeing the significant warp, where the top is a lot more even. And we were able to utilize kind of the same thing, the Reynolds number versus steel hotspots, basically showing the same exact thing, where you have some significant hotspots right at the center of the top of the part, where ours, you're seeing basically a consistent temperature with a couple hotspots here and there, basically at the end of flow. So for the last case study, we actually utilized Moldex to simulate conformal venting and conformal cooling. We had a customer, a new part, they had a prototype tool, it was aluminum, but they were having a lot of issues with like voids and sinks and just non-filled areas. So what we did was, again, we ran different scenarios to make sure we're replicating what the customer is seeing. We're seeing voids, sinks in Moldex 3D. But Mantle helped us, or allowed us to throw in these conformal cooled lines and conformal venting to basically follow the contour of the part. So with those printed Mantle cavities, we were actually right off the bat, the first shots, the parts had no issues at all, removed all voids, removed all sink. Moldex allowed us to implement these solutions and feel more confident moving forward in order to give our customer a solution, a great part. So those are my 3 case studies. Not sure if there's anything else, Ethan, you wanted to discuss.
I think that's great to share. Thank you, MJ, and apologies if I was cutting out before. Sorry about that, but happy to take any questions now, MJ and I both, about obviously anything we talked about here today. And I think we'll be sending out a copy of the slides as well as the recording. So sorry again, but thanks for joining, everyone, and happy to take any questions now if there's anything we want to chat about.